Uh, Welcome all. Welcome to the 10th session, live interaction session. Um, let's wait for a couple of seconds for someone to join. Let's start our, well, not couple of seconds, couple of minutes. Let's start our session at 6:05. So it's 6:02 right now. Let's start at 6:05. So let's get started. It's still one more minute. Let's wait one more minute. Right. So let's get started. So I was basically looking into something I was doing, some code and stuff. Anyways, so welcome all to the 10th session of live interaction section. Uh, there are a couple of loose ends that we have left. We were discussing things like numerical linear algebra, specifically SVD. Turns out because every time I also did not plan the session properly, as like structure it in a proper what do you say, proper like a lecture. Uh, we kept on swinging from one topic to another because of certain doubts. And for that, and because of that, we had to now basically abandon our pursuit of discussing numerical linear algebra approaches and stuff. Um, yeah, so that is where we are with this topic. So went into stability of iterative methods last time. Kind of that itself, I was not able to conclude in the last lecture because honestly, it's a lot of theory and lot of things that can be discussed in there. So that is there today also. So basically, today uh, I'm planning to focus on one human stability analysis, something where we can move forward with this. So, anyways, so before I do that, before because there is no audience as such right now, let me try to also go ahead and yeah, go ahead and just show you one more advantage of SVD. That was some material I had prepared, uh, which I have ready with me. So let me just discuss that briefly before getting into it. It's basically now we don't have a lot of time to spend on numerical linear algebra. Planning to look into physics informed neural networks. That is something that I'm trying to work out. Uh, Anyways, that I'm planning because we after this session we'll be left with two sessions. Session number 11. This is session number. I think this is session number 11. This is not session number 12. Let's check that as well. I'm not sure now. Got confused. So is it? Let's see. So this is the one. How many sessions have we done? I think this is the 11th session. Uh, yeah. Okay. So we have I think 15th, Wednesday next week. So we'll have roughly 4 hours to discuss physics informed neural network. And the idea will not be to go into details again because I'm not an expert in the field. It is a sort of learning together kind of thing. But what I feel could be a unique approach to looking into physics neural network, specifically discussing like attending a live interaction session. Something unique could be getting to know or at least introducing neural networks or AI from a mechanical engineer's perspective or for any non-computer science background. What are some basic questions and can we answer those questions quickly? So those at least the first part of it is uh, towards that. Basically, we'll start with the small what neural networks are quickly. We'll do it quickly, not into depths or anything. We'll The idea is that I will generate a chat GPT code to run a physics informed neural network, or if we have that already, we'll just go through the code once line by line, see what those lines are essentially doing, but then take a bigger what do you say bigger picture context of what those lines actually mean. So just not following through the procedure of training a neural network and stuff, but just discussing essentially what every line, like what is the procedure and what every line is doing in the whole big scheme of physics informed neural network training, and then how could we use it in like that. Um, with that, so, hello Apurv. Actually, we'll be discussing physics informed neural networks in week 12 and 13. That is something that I was recording for the session. But today I was planning to tie all the loose ends that we have left. So as you are aware that we have not been able to uh, properly structure or discuss this numerical linear algebra part. I have some small material ready with me. I don't want to dedicate the entire, again, dedicating entire 2 hours into closing this session. Some quick material, I have 10 minutes material on SVD. We can discuss that part as like basically a code on that. And what else do I have? Yeah. And then we can discuss this von Neumann stability analysis. This is something that you might be interested in. This would be a good closing of what we had discussed last time, that is the stability of iterative methods and how do we actually. So Scarborough criteria, what we realize is a conservative criteria. It is a necessary condition. Sorry, it is a sufficient condition, but not a necessary condition. So what that means is you can't reliably use it to judge the stability of your scheme, the iterative scheme you're used, or what do you say, the scheme you have used or the discretization that you have put in. So that is there. So von Neumann stability analysis can work if you're lucky, and which is generally which could be a which could have a good probability. Even if your boundary conditions are periodic in nature, then turns out that there is a sophisticated, nice uh, Fourier analysis based methods to explore or study the stability analysis. And this is, you remember I was mentioning that at some point of time when we had first taken this question on Scarborough criteria, I was loosely talking about I was searching for a book where analysis was done, where they were discussing the 1D heat diffusion equation, unsteady heat diffusion equation in one dimension space. And I was talking about something where you calculate the error, and there you basically are trying to figure out how the error is affected by the discretization scheme. That is, I was trying to search for that book. I couldn't find it, but essentially that whole topic in that book was about von Neumann stability analysis. Turns out I was still not able to find that book because it was long back when I had referred to it, and I lost track of the book. Anyways, the topic is profound, and it can be found in our multiple set of books. So our purpose suffice. But just before doing all that, just let's quickly run a piece of code which I had uh, written down for the purpose of that numerical linear algebra. It's a small code basically trying to close that loose end on the numerical linear algebra stuff. Just give me a second. What's the issue? Okay. So uh, well, I'll open up I'm opening up my Jupyter library, Jupyter notebook, and then we'll run that code. I'll just quickly show you that actually it turns out that we an important part that we didn't actually discuss about SVD. Again, it has now become a little what do you say, repetitive, that I have been coming back to SVD but not closing it. But still, let's one last time, let's go to the SVD part of it. It's actually very interesting to see, and we can actually see through this code that SVD is indeed a very stable system. So it has a geometrical picture. That is one importance of SVD. Then there is another issue. Then there is a universality aspect of it. And then there's a computational stability. So we will also explore, we'll just quickly witness how that computational stability is in place. So let's quickly just see that. Um, so SVD and intro, I don't remember there is, yeah, ill conditioning. So basically, SVD shines in the face of ill conditioned matrices. What you will notice, just give me a second. Yeah, no, just give me a second. Right. Okay, so as I was saying, so ill conditioning, in face of ill conditioning, SVD kind of shines, and I'll show that to you. So we'll talk about, briefly, I'll introduce Hilbert matrices. These are kind of very they're canonical ill conditioned matrices. High degree of like the condition number is quite high. So what is what is condition number? Condition number is the highest eigenvalue divided by the lowest eigenvalues. Uh, Indeterminable matrix, or the determinant of the matrix, which the determinant of a matrix is zero. So you know that one of the eigenvalue is zero, and when we say conditioning number, we mean magnitude, because eigenvalues also have complex components. So in that sense, the lowest eigenvalue is zero because it is the lowest magnitude you can have. And that is what the condition number of a indeterminable matrix is infinity. So that is like the worst kind of matrix. But you can go close to it and not just reach an indeterminate situation. And that could be the case of a Hilbert matrix. So this is how a Hilbert matrix looks like. The condition number is quite high. You see, it's in the order of 10 to the power 5, and it depends on the number. Depends on the size of the matrix. So uh, early small dimensional Hilbert matrices are not that ill conditioned. They are fine. But when you increase the size of it, it goes quite high. And what that does to you is that certain other decompositions, like our LU decomposition, which we are very familiar with, they just fail. So I'll show that to you. So for a Hilbert matrix of size 6 by 6, if we try to solve AX equals to B, uh, if we are taking x to be so we have kind of um, just to demonstrate the fact, what are we doing is we are trying we'll be solving ax equals to b, but to just make up a problem of ax equals to b, we have we'll take a x, we'll create b, and then from a and b we'll try to recreate x. Okay, so we have a x2 which I have taken as this. It looks like this. Nothing very, what do you say? Uh, yeah, it is not very, we can take it anything. Let's take it as this. And let's see if this one gives anything. Just for the sake of, in the case that this kind of is not able to demo. Oh, can I slightly zoom in? Yes, I'm sorry for this.
Yes, now it's okay. Yes.
Yeah, I think this is fine, right? Just for the case of if this my for this x this value of x2, if my demonstration does not work, just for that case we'll keep the original one, for which I am pretty sure that this will work. So in that situation, now what are we doing here is, we'll first I'll just show you the x2 value, then the condition number of a, and then we'll calculate. What we'll do is, the way this uh, inverse is done using Gaussian elimination. The logic is from LU decomposition. So P is the permutation matrix, I believe. Uh, it's called permutation matrix, which is basically a matrix which dictates row transformations. Yeah, row swaps and additions. Basically, it's not additions, it's just row swaps. So you can swap rows with the permutation matrix. Say that somewhere. And if not, that is what the permutation matrix is all about. You do the PLU decomposition, then you solve the x value by saying basically saying what? So if your A is broken as PLU, x equals to B, then the way you solve x is, you say P multiply P both sides. Huh? Just give me a second. So L, yeah, you solve for Lx equals to. Oh no, wait. So the way this is the decomposition. Let me. So this is the decomposition. PA equals to LU. So in that sense, if AX equals to B is the situation, then you multiply P both sides. Uh, then you get PAX equals to PB, and now you break PA as LU. So now LU is equals to this thing, and so you find X equals to PB. And LU, now LU can be done using Gauss elimination. And that is what I think is used by this NumPy linear algebra solve as well. So you find, what do you find? You find, I think, yeah, Y is, so LU, right? So what we are saying Y equals to UX. So you say UX is equals to L inverse, or roughly like basically solving for UX. And then how do you solve for UX? How do you solve for X? You say X equals to UX equals to Y. So that is the logic. So these are the two equations. So first you solve for Y, which is like Ly is PB. So L, this is how you solve for Y first, and then you find X by using U and Y. Okay, so this is how you will do it. And then we'll print the solution that we get and the norm also. So the error which we get. So basically, I think this is square root mean squared error. Mean squared error. Yeah, mean squared error, right? MSE is, yeah, mean squared error. It looks like it's not mean squared error, it's root mean squared error, RMSE, I think. NumPy norm, right? Norm is defined somewhere. NumPy, yeah. Let's look at what NumPy linear algebra norm. What's the formula for the norm they use? Because norm has a lot of formulas. Okay. Yeah, this is the formula. Root mean square, right? Root mean squared formula. And then let's just check how NU performs. And then the other way, then what is the other way? What is the SVD way of looking at it? Okay, yeah, so let's look at the SVD way of it. Okay, so the SVD way of it is you write AX equals to B and you do a decomposition of X into U. Then S is the diagonal matrix, and then there is a V transpose. So V transpose will be there. And the logic is U and V transpose are orthogonal matrices. Now the property of orthogonal matrices are that U transpose is U inverse. Are you aware of that fact, Abur, or should I discuss that?
Sir, can you repeat, sir?
I was just saying that for our orthogonal matrix, the identity holds that its transpose is its inverse. So like
Yes, sir.
U transpose,
Yes, sir. That's okay, sir.
that's okay. So if we multiply U transpose both sides, what do we get? We'll get SV transpose X equals to U transpose B. And then again multiplying, yeah. Then what do you do? Then SV transpose. So now S can be broken off because S is a diagonal matrix. So you S inverse is just straightforward to calculate. So then you go again. So this is the SVD way of calculating AX equals to B. That is what I'm trying to show to you. So then you get into this kind of region. U transpose T, U transpose and B, and then finally X becomes V S inverse U transpose B. right? So this is the SVD approach, where because of the orthogonality property, we can the inverse is quite straightforward. Like the inverse is the solution can be straightforward. And now we are going to compare LU decomposition solution with the LU decomposition versus the SVD decomposition. So just let's look at the implementation of this thing in this code. So you find US and VH. VH is the V transpose. Okay, this is VH is V transpose here. So now your A inverse, you can call it A inverse, or you could just directly multiply B with this entire thing to find SVD. You do the same thing as I told you. This is the this is the V multiplied by S inverse. This is the S inverse part, and this is U transpose. And then you multiply, you find X based on this thing. Now there is another thing. There is one issue is finding the right solution, and the other issue is the stability of it. Suppose there are there are round of errors you have in computers, right? If you have some round of errors to some small degrees, uh, how does your solution deviate from your true solution? Does it deviate from a true solution? Okay. Now, that is also something that we will look at. So in that case, if suppose your B gets perturbed or B gets a little distorted, the true B value gets from the true B values because of some round of errors. We kind of suppose some error is added. Suppose so we are adding error only at the first entry. Okay, a small only at the first entry we are adding some error. Okay, and now we'll see how the from the LU decomposition only how the perturbed solution looks like. So there is a perturbed solution, there is a true unperturbed solution, and that happens for both LU and SVD. Okay, so let's look at it. So I can just remove these things. Let's see. I don't know how things will work. So condition number of A is what? N to the power 8 for a matrix of 3. Okay, if we go for a small matrix, let's say 3, then there is no issue. The true solution, let's look at the true solution. LU decomposition gives you the exact 1, 1, 1. LU decomposition with the perturbed solution is also very close to your true value. And for SVD, you get similar, entire same thing. But for, let's say 6, what happens? So the true solution is 1, 1, 1, 1. But the LU decomposition, look at the LU decomposition result. 2, 1, 2, and some absurd large numbers. That perturbed solution is also large numbers. And it is kind of same, I feel, right? It is not different. A little different here. There are some differences. Yeah, but both perturbed and the perturbed solution, the solution by the unperturbed solutions are largely deviating from the true solution. Let's look at the SVD solution. SVD solution is 1, 1, 1. So SVD solution gives you the correct value. And with the perturbed value, the deviation is not large. Deviation is small. So if you look at the norms, compare the norms here, order of magnitudes difference. And we can actually look at it. We can just plot it also. So if I just plot this whole thing, is this okay? So yeah, let me color this. Basically label this. So what you can see is that the SVD and the true solutions are kind of overlapping. You can't even see the true solution. It's overlapping over the SVD solution, but the LU solution is kind of deviating. And no, wait, this is the SVD only. This is not even LU. This is SVD unperturbed. SVD unperturbed. Wait, perturbed. So the perturbation is there. There are some issues. If you perturb it, obviously the solution is gonna change. But how much? Does it change? Does it change excessively? Okay, unperturbed. And yeah, and then also look at LU decomposition. So look at the y-axis. Both unperturbed and perturbed solutions this time kind of overlap now. They are overlapping. So both solutions are kind of equally bad. But in this case, at least your unperturbed solution is not, first of all, it's exactly the same. And your perturbed solution is not that bad. It is roughly bad, but it is not that bad compared to, like, it's several order of magnitude, million times better than LU decompositions. And that happens because you see naturally, this happens because in your SVD solution, as I showed you, we are breaking things into orthogonal tensors and stuff, which the inverses of which are well defined. Okay, these inverses are also well defined, and you have a diagonal matrices, and the conditioning number issue kind of gets resolved because now it's easy to take inverse. The inverse is straightforward, and you don't have to numerically do it. So this is called, I think this is called pseudo inverse. So this is the pseudo inverse technique of SVDs. Let me check. Or is it not called pseudo inverse? I might be wrong. I'm not sure. So this is the pseudo inverse. So basically this is V transpose. So D plus is the D plus is basically 1 by diagonal matrix. So all the diagonal values, so 1 by that thing, and then U transpose. That is what we have done. So this is called pseudo inverse. Okay. So it's actually very powerful in pseudo inverse kind of thing. So there was some demonstrative, like some code that I have written down just to demonstrate the strength of SVDs. We only had time, and I prepared only for that part of it. I don't want to go into lot of linear algebra also, but yeah. So not discuss. We'll only discuss this much for numerical linear algebra. Definitely, I have motivated enough the use of SVDs. Maybe you can go ahead. Maybe if you ever find an opportunity to look into these things, you can you can pursue them. So that is one thing. Today, what are we going to do? Let me. Is there now today? Let's get into. I have to open the book which I have to refer with. It's a good book. Uh, yeah. The book's name is share the DOI. They don't have an option, is it? That's a good book. Okay. Numerical methods for partial differential equations, finite difference and finite volume methods. Majumdar. It's a good book. This was the same professor whose FD, M and FVM paper we had discussed. So coincidentally, I was looking for some material. This way, actually,
I think
last
his video lectures are also there on YouTube.
this professor, huh?
I think so because his name sounds familiar to me. I think
Let's.
he's middle-aged person, not very old.
He is not very old. He is quite young. Not young, but at least. So Sandeep Majumdar, let's check. Guys, his books are, so he has provided lectures, huh? Nice. Amazing. Great. Yeah, so we can explore that as also. Nice. Good. I didn't know that. Nice. So, anyways, let's again repeat what he has discussed in his book about. So, where we had left last time. So, what we saw was essentially whenever we are solving for we are kind of replacing ax equals to b because it becomes cumbersome when your size of ax equals to b becomes large. When you have millions of elements, it's become prohibitively expensive to directly solve for ax equals to b, and there we go for iterative solvers. Now iterative solvers, no matter how they are, you essentially break them into basically what you're doing is either you are or at least in the case of Jacobi and Gauss-Seidel methods, you are kind of substituting certain values midway of your solution. So essentially your ax equals a breaks down into L plus D plus U, and depending on your iteration scheme, you can actually write your iteration scheme in terms of L, D, and U and B. So your next so your next step, so every iterative step, you get a new set of values, and that there is a iterations scheme that you can write. Now, from that iteration scheme, if you try to calculate how the error propagates between iteration steps, you will essentially be able to write ek plus 1 into some matrix times its previous iteration value, and it is essentially the eigenvalues of this matrix a matrix that decides your stability or convergence criteria of your scheme and your discretization, because now discretization comes in from the coefficients of a. Okay, so the discretization has that discretization effect is coming from a, and your solution scheme or comes in this iteration scheme. But now finding the eigenvalues of your this iteration scheme or this matrix alone is again a heavier task, especially again if your A is of million size. Your this matrix will also be of million size, and essentially finding the eigenvalue of this matrix is again similarly heavy task as finding Ax equals to B. So now what can we do? Again, this method is fine. This is a good method, but this is not, again, fails in the face of large matrices. And in this backdrop, we kind of can introduce the von Neumann stability analysis or the Fourier analysis. Yeah, I need to refer to this book. Fourier decomposition of error. And let's talk about the logic of it. So, are you aware of the Fourier transform of matter yeah, just Fourier transform?
Yes, sir, but I'm not very like not very good at
But
it.
but you know that there exists some kind of Fourier transform.
Yes, yes.
Great. So now the logic here, let's before we get into the details, let me rather spend a little like few seconds on the logic of it. Acha, before that, do you have any questions or anything that you need to discuss or no, right?
No, sir. You go on, sir.
So what is the logic there? So Fourier transform essentially are for signals which have a period, which are periodic in nature, and the formula for that, I'll pick a form like a picture where the formula is a little simpler. I don't want to scare people because with more number of graphical like this Greek terms, it becomes difficult to appreciate what is going on. Open image in new tab. I find this one fine. So this is what the Fourier transform is. If you have a signal or any function, let's not call it signal, again, a new jargon. If you have a function which is periodic in nature, it does not actually matter. So if you think if it is not periodic in nature, your integrals go from minus infinity to infinity. But if it is periodic in nature, then this integral becomes tractable. You can actually integrate it, and you get this kind of form. Okay, e to the power minus j omega t. This arises from a linear algebra kind of, linear system analysis. Okay. Uh, and what essentially you're doing is, if you have a signal, you want to break it down in terms of frequencies. So a signal, basically now the reason I'm calling it a signal rather than calling it as a function is that I want to associate a connotation of time as the independent variable. And with time comes the connotation of frequency. But in our case, it does not matter, because at the end of it, there is an independent variable and a dependent variable. But in the context of Fourier transform, definitely there is a frequency component, right? So what a Fourier transform is kind of doing is, it is kind of, wait. So the way to,
Transforms it into another variable, just like
yeah,
Laplace.
it's a transformation, definitely, but there's a good, nice picture that I can actually discuss, which is quite intuitive. Just give me a second. I'll open that book where the part is discussed. It essentially tells you that if you have a signal, how much frequency content of certain frequency does that signal have? So let's look at the Fourier transform of sine x. Sine x, okay, or sine t. So okay, let me ask to you. Sine, is it this one? Right, this one only, right? Does the Fourier transform of sine x look like? Should look like this. So what is the Fourier transform of sine x? Let's first ask AI only, let's ask. No, somewhere it would be given, no? Yeah. So, okay. So let me ask to you, what Fourier transform, the physical understanding of what is going on there. As you mentioned, it is a change of variable. It is a transformation. It's not just a simple change of variable. You're kind of transforming the variables. But what is that transformation doing? What is the physical understanding of Fourier transform? The understanding is, it kind of gives you that if you have a signal, let's talk in terms of signals now, and let's bring the connotation of music also. Music are the music has signals, right? Sound waves have frequencies and wavelengths, uh, and we hear music, and music has a lot of sounds are coming in the music in music, and they vary with the frequency, right? uh, Different instruments will have different frequencies. Different sounds will have different frequencies, right? And when you hear them in together, if you hear them together, uh, they are pleasant. And sometimes, actually, if I play a music to you, you know that this sound is coming from guitar, and if I play it using piano, you can tell me that this sound is coming from uh, piano. And if there's a full orchestra going on, you know that there's a piano component, there's some vocals are also there, someone is singing. And I think the whole point is that every instrument has its own frequencies. They can be multiples. I feel not very technically, I might be technically wrong, but I feel every you can actually make out from a sound signal that there are high frequency components or if it is a low frequency component. Just to say, we know that how a low frequency sound looks like. It is a little dull. It is a heavy tone, right? We call it a baritone. Whereas if you have a very high pitch sound, you know that it's a high pitch sound. And what is going on there? You are kind of able, you're being able to, from a, let's say, mixed noise, you are able to figure out that there is some high pitch components in your sound and there are some high pitch, low pitch components of a sound. And what essentially is going into your ear is not 100 sounds parallelly. It's one signal, which, as you know, signals will interfere, differ, they will add up, right? Signals add up, right? If they're coming from different sources, when they reach in your ear, the sound signal will look some weird form, right? It will look in some weird form. Let's say let me draw something. But at least we know, and when we are hearing music, we know it will be periodic. At least we are aware of that, and it might look something like this, and it might look some kind of. And let's say this is the period. So after this, it starts repeating itself. Or yeah, maybe something like that, so that it repeats itself. Okay, okay, something like that. Now you know that there are some high frequency components and there are some low frequency components like this. In this region, you know, and I have not drawn it perfectly. This is not technically right. If there are high frequency components in the sound, they will even persist here. So what essentially, if I just add two sounds, a high frequency sound and a very low frequency sound in different amplitudes, this is what it will look like. Let's do it on Desmos. That would be better. So if I just simply add 5 sine point x 0.1x plus, so this is how this one will look, plus 0.02 or 0.3 into sine 10x, or let's say 2x. This is how your sound will look like. 2x is very bad, huh? This is very low. Yeah, this is better. So now you know that there is a low high frequency component, and we can do even better. We can go minus cos. And if I talk in terms of x, if I put it as t, then you know this is like I'm talking in terms of time, right? Cos 5x. Now it becomes, at least from earlier, you could actually appreciate that there is a low frequency thing happening. Like, you know, the period is not, if you look at this sound signal, this is not periodic. The first period is indeed something like, should be what? 2 pi divided by 0.1, no? No, into 10, 20 pi. See, it's 20 pi, exactly 20 pi. You know that there is a large wavelength stuff going on and there is a small wavelength stuff also going on. With this, it might become unclear what is that frequency. If we even do something else, let's say 12, then it becomes even difficult. So the way I'm introducing Fourier transform is the other way. Like generally you consider a general signal and go into breaking it down into different frequencies. But I'm just to give some intuition, we can do better. Let's say so something like this. Now you know that definitely something is going on, but now you can't at least visually make out what are these components. Now Fourier found that you can actually break things down into components because of the orthogonality property of these sine and cosine functions. So what happens is if sine kx and sine mx are integrated over its period, over a large period, let's say minus infinity to infinity, what happens is this will be zero if K and M are and K and M are integers in this case, let's say K and M are integers. So this integral will be 0 if K and M are not the same. And if they are the same, then you can if they are the same, then that integral will have some finite value. So just let's talk about orthogonality property also. And a lot of like Bessel functions, and then these uh, even Fourier functions. What you remember? We had this question of eigenvalues. So we get eigenvalues when we were talking in terms of that eigenvalue problem. It is these orthogonality properties that allows us to find coefficients to this for a general solution in 2D or 3D space and also in time when we have a linear equation. Okay, orthogonality property of sin x. So were you aware of this? Whatever I have what I'm discussing, are you a little familiar with it?
Yes, yes.
Okay. So just want to see the proof. Yeah, so proof like this. So basically L is now the period. So the whole integral is now basically reduced and normalized in terms of a period of this function. No, the idea is if you have a cosine in your function, and if you multiply it by the same m, so you multiply it with random m value, it will have the integral 0 if it is not the same. It will have some finite value if they are both are same but not 0. And if they both of them are 0, then you get a different value. So if such integral does not exist, if such sine function or cosine function does not exist in your musical signal, which you are talking about, then you know that then there is a different answer to this integral, right? So for all other frequencies which are not n, the error will add up to 0. For frequencies which is for the frequency which is there, let's say n is the frequency, then only for that n value you will get a finite L. And if that n value does not exist in your signal, then you will get 2L. Now, if you do it for all n values from 0 to infinity, you get Fourier transform. You can actually, and that if you do it for all frequencies for all n values, now n has to be now linear, this n has to be continuous. Now this becomes, instead of talking in terms of integer or integers, we talk in terms of um, continuous or real number. N can be a real number also, right? In this case also, we are not saying that n are integers, but just to introduce this thing, I have mentioned integers. Here I have taken a non-integer also. So now the idea is you multiply your entire signal, whatever you have with a cosine function. You know, e to the power minus j omega t have sine term and cosine terms, and you integrate it over minus infinity to infinity, and that will give you the amount of what this integral does is it tells you the amount of content that particular frequency has. So for example, if I take sine x, the Fourier transform of sine x, what do you expect? That for all other frequencies, only the Fourier transform will be a function in omega, right? So for all values which is not 1, the Fourier transform, which is a function, will have a functional value of 0, and it will only be uh, some value at x equals to 1 or omega equals to 1. And that is what happens with sine x. With cosine x also, you kind of get something similar. See, similar at omega naught. If the function is omega naught, your Fourier transform, if you calculate it, it will peak at these two values, minus omega naught and omega naught. Again, the logic of minus omega naught is just from the construct of it. negative frequencies don't make sense, but the mathematically you will have negative frequencies. And so the way this Fourier transform is constructed, you will have negative values. And that is what the Fourier transform does. Okay. Now we'll apply the same idea to our error kind of thing. Okay. Now, again, one more thing that you would notice is that we kind of need a periodic signal. We need periodic signals. Any non-periodic signal will have a what do you say? A frequency of infinite frequency, but that we can't deal with this Fourier analysis. We'll discuss that. So I'll show that to you. But let's say this method can work nicely if if you have a periodic boundary condition. Okay. So now the way you look at it is, suppose you're solving a solution in 1D space only. Let's start with 1D space. Then, as in context of how we were discussing the Fourier transform, okay, let's first understand that there will be a solution y of x. Then so there will be a true solution y of x, and there will be a solution which we approximate on numerical scheme or numerical method. Let's just call it a simple y. But now, because of our discretization, we will not have a y value at every x location, but only at particular nodal values. We'll call it as, at the nth nodal value, we will have some x. And from that, you will get the error. Okay. Again, at the nodal location, nth nodal location. Now, in the context of Fourier transform kind of thing, this is how the Fourier transform essentially looks like. You will have these integers, a to the power n n, and similarly sine term will also come. So that e to the power minus whatever we saw, basically we are saying that it will have all kind of frequencies. Okay, and because we know that there is a period in our so essentially what happens is, if you have a period in your period, if you have a periodic signal, then you know that that only that like what you say, only that integer multiple components will have to have. Like if you have a period, then no matter how final your solution is, all your higher component terms in your in your signal will be integer multiples of your lowest frequency. That is the logic there. So it can be twice, thrice, but because you have a period, a general non-periodic signal might not have can have linearly independent frequencies, but for a periodic signal, it is known that all other higher frequency terms will have will be linearly dependent on the lowest frequency. Okay. Okay. And this, and if you can imagine when this can happen for the case of, let's say, boundary conditions of um, y given Dirichlet boundary condition given at both ends, the error is zero. Okay, so your frequency is kind of defined. The lowest frequency can be 2 pi by L, right? So in that context, we can actually shorten this and write it in terms of exponential terms. Okay, so let me do that also. Directly written that down, but no worries. No worries. Like, no, not a problem. E to the power, the same thing. Mx by L. Okay. Now I is the iota term. Now let's this n is what? Let me check down. Okay, so this n, let me correct this fact. This n is not at the nth value, but error at the nth iteration. Okay, I'm sorry. This is the nth iteration solution. Okay. Now let's look at, because we have a discrete points only, right? We have the solution at the discrete points. So errors will also be the discrete points only. Let's call the node value with this. Let's denote the node value with the jth subscript. So if we just need to substitute that in this kind of formula xj, okay. J is kind of, we can calculate xj depending on what the node number is. So xj is actually, xj will be j times delta x, where delta x and j will range from what, 0 to, let's say, suppose there are m number of nodes, capital M number of nodes. Okay, confuse this m with small m. Okay, suppose this is the number of nodes. Okay, I don't want to change notation midway. I'm using the notation in the book, so I'll keep on. We'll stick to that notation. Then actually we know that j ranges from, it's basically j times L divided by m minus 1, because, and wait, and j range from, j basically is in 1, 2, and so on to m minus 1. Let me check why m minus 1, because we start from 0. Basically, we are starting from 0. That's why, because our first node will be at the boundary. Okay. Now, if we substitute that in here, and we break this notation as saying e to the power j. Like we put the subscript to emphasize that it is at the jth or jth node. Then only change will be we substitute this thing as j divided by m minus 1. LL gets cancelled. Okay, so now you see that there is a phase angle kind of coming. Now this whole thing is going from 0 to like m times j. M is, let me take m also out. If we move in j, if we traverse over j, we know that j starts from 0 and ends at pi, right? It ends at pi. So essentially, this is a phase angle associated with every location. So every location, every jth location will have a phase, which we will call as, or what we can do is we can take out j also out and just call this as a constant, right? M thing. So that this becomes a constant. So you now have ij and some theta, which is a function of m. Okay, depends on m. Okay. Now, as I told you, m can be m is the lowest frequency because m is associated with what? M. What is m? M. So what is theta m? Theta m is m pi by m minus 1. Okay. So basically what that would mean. So suppose what this theta m, what is the uh, period of this what is it denotes a period, right? It denotes a period. This is the lowest period. So for m equals to 1, this is the period it will have, right? Pi divided by m minus 1. At let's say at j equals to m minus 1, that will be the lowest period, right? As I mentioned, if I put j and so I is, note that I is the iota term. We know that for j equals to m minus 1, you get the period of pi, right? So that is the lowest period. That is the lowest signal that is the lowest frequency of the signal we can have in our solution. Okay. For higher m values, you will have finer sine wave. So if I were to just plot, or let's just skip it. I think you got the point. Okay. Yeah. Now, something which I had skipped was here when we had discussed this entire thing, we were discussing the eigenvalues should be was these eigenvalues. Okay, so we talked about, so basically when we were looking at the stability matrix part of it, you might have to go back and see. We were talking of a matrix exponential, and we realized that depending on the eigenvalues, if eigenvalues are negative, then your solution will be your the eigenvalues of the matrix exponential will be less than 1. Okay, otherwise it will be greater than 1 because we are kind of taking the eigenvalues of a matrix exponential is the exponential of the eigenvalues like this. Okay. Now, this is something which I have not discussed properly. So anyways, the whole point is that essentially we are not interested too much into the entire range of eigenvalues, only the one with the largest, what do you say, largest norm or largest magnitude is the most important eigenvalue, because all other eigenvalues will have lower lower magnitude, and if that highest eigenvalue is below less than 1, then we know that this solution will be stable. So we know only the highest eigenvalue, and that highest eigenvalue is called spectral radius of convergence. So a lot of terminology is there. This is what it is. Maximum of the eigenvalues. Okay. Because for that matrix, you know that then all other matrices will be negative only. Okay. Uh, and the solution scheme will converge. That is the idea there. Okay. Right. So now the logic here is whatever we have done. Yeah. So basically what we are going to do is we are going to substitute um, this representation into our iteration scheme and check and then from there we can actually kind of we will get the maximum of the eigenvalues. So let's look at it. How do we get that? Okay. So just to I think you kind of following, right? We'll come back. So the logic, let's start with the Poisson's equation. For example, we'll demonstrate how to use this representation to check the validity or check the stability of a iterative solving scheme. Um, so basically what we are trying to solve is, let's not take y, let's take z or theta, not phi, let's take phi. So this is the Poisson's equation. This is not the Laplace equation, okay? We're talking of some source term, there is some source term. And we know the solution, we know the finite difference way of solving it. Okay. So what is the finite difference way of solving this? Okay, and we'll do it in 1D only, not the 2D case. Just this simple thing. So what is the central difference scheme says that you say phi j plus 1 minus 2 phi j and then plus phi j minus 1 is equals to Sj, and then if you just redistribute things, just uh, you get is small redistribution. Just to make this coefficient of ij 1, and there will be delta x square. Sorry, okay, 2 delta x square. There is no 2 here. Right? There is no 2 here, right? Right. So now this is our AX. We are now at the stage of AX equals to B. So just to now start demonstrating this Fourier decomposition of error. So we have just decomposed the error into its Fourier components. That is what we have done into sense of wavelengths and stuff, right? And the wavelength is associated with the or frequency is associated with the sharpness of the features that will have. So sin x has dull features, but sin 10x has very sharp features. In that sense, I'm talking frequencies and sharpness. From that sense, I'm talking. So at this stage, we are at ax equals to b. Now let's go into the Gauss-Seidel. Let's say if we go into the Gauss-Seidel sense, Gauss-Seidel way of solving it iteratively. Then again, you go back into writing that into L and D and U, and you write as phi j. You remember the notation that we had taken earlier. N was the nth iteration value. So phi j n plus 1. You know the previous values. So phi j n minus 1 into, you would know the previous value. So n plus 1 will be here. This will be n plus 1. And then you find this thing as Sj, this entire thing. And you use the value that you would know is phi j plus 1, and that you will use from the previous iteration. Okay. Just the previous iteration value you will put for phi j plus 1. Okay. Again, same breaking it down. We are basically going into this form, this kind of form. Okay. But it does not help us in Fourier decomposition. It does not help us to go into a matrix form. So it's better to just stick to this iteration scheme kind of expression. So the exact solution, let's also put exact solution, how the exact solution would look like. Exact solution will be where the iteration scheme will just converge. How would the converged solution look like? It will look like this. Right? Yes. Now you subtract this so that you get errors into the framework. Now, if I do that, I'll have this. Now, you're following, right?
Yes, sir.
J minus 1. And then this SJ gets cancelled. So we only have now like that. We are kind of, I'll tell you what do we have. This is n plus 1. This is also n plus 1. And this is j plus 1. Okay, now at this point, where are we? We are kind of somewhere where I had mentioned, we are kind of saying that in some crude sense, dE or d epsilon by dt is some b times epsilon. Again, here epsilon is a matrix, is a vector. Okay, kind of here, and so essentially, if we solve for it, we will kind of get epsilon is e to the power bt. Now, what is t? T is kind of some which is like it's a function of n, right? In some sense, t is kind of representing the nth nth iteration. So that is what I was talking about, that this an E0, this I was trying to put. Note that this is a matrix. This is not an exponential. This is a matrix exponential. This is what we call. And this will depend on the initial error, and it will converge depending on the eigenvalues of B, which have to be negative, and the eigenvalues of e to the power of B of t have to be less than 1 magnitude wise. And only the maximum, the spectral radius, which I talked about, which is the eigenvalue with the maximum magnitude. If that magnitude is less than 1, we know all eigenvalues are negative. So now we are at this form. Now we are in a position to just substitute this thing. Okay, substitute this here, and we'll see some things. We can start some analysis around this. Okay. So if I just copy paste this entire thing. Okay. Okay, one more thing, one step which we skipped here. Yeah, one important step which we missed was that we kind of did not note this infinity is the problem. We can't deal with it right now. We have to simplify it. So my only point is, suppose that you have a grid. We know that the highest wavelength is this, but what is the lowest wavelength? The lowest wavelength can be only this, right? And that means that there will be M-1 periods in your not even this, wait, not even this. So not even this, just this. Let's say some sine function is there, and then that repeats. Okay. Now, so the lowest, highest frequency we know is not just infinity, it's actually M-1. So if I go back, we can actually reduce it, because that is our limit of discretization. That is where our discretization is kind of coming in. Okay. That is the highest frequency that we can actually deal with or represent, for that matter, with our number of discretization. So this is where the size comes in. Okay. Your grid size comes in. So now this is where we will use, this is the formula that we will use. Okay.
You have to take just one term of that, one term of the summation.
Could you repeat? What did you say?
You have to just take one term of the series, then you have to substitute in the error, because that one term will it will have the same nature as that of the entire series.
Right. Wait, let me understand what you said. One term as in any one term in that series. So for any m value.
Yes, sir.
Right. It happens. Yeah, that happens. Yes. Only the first term it is. But can you explain why?
Because individual terms make up the entire series, so the nature of one term will be same as that of the entire
Yeah.
series.
They are linearly independent. Yes. Just I, J, you have to substitute. So let me do that. So by virtue, as you correctly mentioned, by virtue of linear independence, e to the power I, iota, I, any this thing are linearly independent. Independent terms, like these are independent terms. So we can just look into the individual terms. So basically, we have Cm n plus 1 and then this thing. A minus 1, right? This should be n. Okay. Okay. Now, as I was saying, either we can do it this way or we could have just done it this way. Uh, yeah, and now we can just divide with e to the power iota j theta m. Let me do that also. One more step. So have Tm n plus 1. This we will have e to the power iota theta m here. Or just this will go. Or
And that time term should also be exponential. Then only it will
which
simplify.
term?
The time term, the time steps, n terms and all, those should be exponential, right? If you take it,
No, it's the iteration. Actually, here time step is not entering. I mentioned this time thing in the context that an iteration is kind of a evolution, right? It evolves over time. So it is only in that context. This which term you're saying?
I
There
mean,
is no time term as such here.
the series of the error term epsilon j n equal to sigma, that way, that thing you have written, right? Cmn e power ij theta m. So theta m,
Yes,
e power ij theta m, that is the spatial terms. Cmn is the temporal term, right? Time term.
yes.
So that if you take it in terms of exponential, then it will easily simplify, I guess. Because if you take n plus one interval, then those won't simplify, right? Cmn is there, right? So if you, what I'm saying is, if generally it is taken as exponential only.
So it's
E,
already taken in. That is what you're saying, right?
yes, I
We'll
mean
have to.
that is how Sir did in the like stability analysis.
Which term did he take? Exponential.
Cmn, so if you go the right
Oh,
side
this is
top,
a. You see, this is a steady problem in this case. So,
no, no,
so the time is not coming in.
no, sir, that I'm not telling. The error term is a summation term, right? Epsilon jn. The
Yes.
Cmn is there. Cmn is taken as an exponential only by sir, by the professor.
Okay, that yeah, but in this case, I think he must be talking about something else because here we have an iterative scheme rather than having a continuous continuous function. It's not a continuous function in time. You're kind of iterating it over number of iterations, right?
That is okay. But
Yeah. So then how does the connotation of time comes? It comes if you treat an iteration by as a time step, then only it will come as a this thing. But wait. So I'll let me just complete that part. Okay. So now we have this thing there, and So what I can do here is take CMN plus 1 common. And then write this thing. But how does it evolve? Okay. So were you raising some other point or is it the same thing? Not
No, sir, same
sure.
thing, only same thing. Yeah,
W minus that.
amplification factor, right? CMN plus 1 by CMN.
Yeah, these are like amplification factors. Yes. Okay. So the way this is kind of, as you were mentioning, if we give a connotation of like n plus 1 as a connotation of time and then find eigenvalues using this map, like analytically find it, or otherwise what we can say is that this ratio should go down. This should be less than what do you say, 1. Okay. Uh, this should be less than 1. Yes, right? Yes, this should be
Yeah.
less than 1. Okay. Now m varies from 0 to okay. So now how does this look like? First of all, let's take magnitude wise. Let's do a magnitude, take a magnitude step. Okay, this can be a negative, positive thing also going on there. So if we just take a magnitude on both sides or norm on both sides, then this can be this can how do we find norm? We can find norm by saying, because it can be in principle a complex number. So this thing times its complex conjugate. Okay, which will be what? The complex conjugate of 2 is remains same. This one will become e to the power iota t, right? And now one more step. So we know the complex conjugate of the top side is 1 to the power. So this one actually is sine theta m. Two minus, and this one will be minus the same thing as plus. So top side, you know, sine square x sine square theta m plus cos square theta m is 1. Here you will get sine square theta m. So let's write that part. So you will have 4, then minus 2 cos theta m. And then cos square theta m plus sine square theta m. So 4 plus 1 is 5. Okay. Now cos theta m. Now this thing has to be less than 1. That is what we want, right? Okay, so what is the lowest value or what is the highest value of this square root? It will be the lowest value will come and when the 5 minus 2 cos x will have the highest value. And that will happen when cos theta m is -1. So 1 by, wait, there will be a 4 here. Is there a 4? Yeah, this is 4. 2 times cos theta m. So now this will happen when yeah, 0. So theta m has to be this value will be negative, right? This theta m, theta will be pi. -1 is pi, right? So theta m has to be pi. Now, what is theta m? Let's go back and substitute what theta m was. Theta m was m pi. Now, yes, theta m was m pi, right? Yes. So theta m will be pi. So yes. So now we are seeing that this will happen when m equals to m-1. This is the for this case, for m equals to m-1, our cos theta value, this entire thing will be what? 5 plus 4, right? Under root URT 5 plus 4, which is 9, 1 by 3. Am I right or am I wrong? Let me check. No, wait. Some mistake I have made. It depends on m. It is not like it's not a constant. Wait. Some issue. What is the issue? Wait. Okay. So the value can go as high as 1. It can be the highest value is 1. When will that happen? When cos x is 1, right? This is the highest value it can get. Lowest value is when it is 1 by 3. So now, if theta, and that happens when theta is this thing 0. Cos theta is 0. So cos x -1, right? Just give me a second. Oh wait, I've made a... So theta m is this, right? Theta m is this. M by m pi by m minus 1. Let's say our m is let's say so let's say our m equals to 2a times pi divided by, let's say 10. Let's say we have 11 points. Okay. Then yeah. So what I was trying to say is that depending on your uh, yeah, and okay. So what's going on? I have a little confusion is there. So this is the function that exists. Okay, and depending on theta m, this value is dictated by the theta m value. Now theta m does not have like a continuous, as we discussed. Theta m exists at these discrete points. Okay. So let's say x equals to k. What is k? So it can be 1 pi by 10. How do I put it? Pi, then x equals to 2 pi, and so on, right? So it depends on your discretization scheme. And finally, you will have pi, right? The largest value will be at pi. Now you see that the highest eigenvalue happens at x equals to 0. Now x equals to 0, for that value, eigenvalue is this thing goes to 1. Now what that means is for the constant term, for the so what does theta m represent? If you put theta m equals to 0, theta m equals to 0 in this error, in this error, what you will see is theta m is 0, so you will get a constant. The error is a constant, right? For that constant term, we know that if our solution is converging, that constant term is going to 0. So 0 remains 0. So its eigenvalue or whatever, this not eigenvalue, this norm stays 1. It does not change. The next important term is this term, m equals to 1. This is the highest eigenvalue. And this value, now higher you go, higher discretization you go, you approach 1. And lower you go, you approach to a lower eigenvalue. Okay. So, and it depends on the number of discretization that you have. So if you have a larger eigenvalue, so essentially what that means is you with the scheme that we have taken, the scheme that we have taken actually converges because its value is always less than 1. If you increase the if you increase the number of points, suppose it's 100, the highest value will always be at m equals to 1, small m equals to 1. Other values will go closer to the lowest value, which is what is the lowest value? 1 by 3, when you mentioned, right? That is the lowest value. And so that is what this method was about. We actually have a table. I have a table to show, to demonstrate this thing. So this is the table from that book. It mentions how with the first theta value, or the first whatever this norm is, this convergence value is, the spectral radius are noted down. You see, if you increase the discretization, always the spectral radius asymptotically approaches 1, but it always stays less than 1. So the solution scheme is converging, and it always converges. We can also say that higher the number of values, the convergence rate is also slower, right? It is not faster. That is also something that we can say. And we can apply this same strategy to a different equation, again with periodic condition. Let's say Dirichlet boundary condition on both ends, uh, and do the same thing. So for suppose, now actually you can just quickly look at the rest of the book. I had to use this book where I was using a second screen to go through this book parallelly. Now suppose we use this what do you call 1D advection diffusion equation. We do the same procedure, and the what we get is that some so there is a P, which is the diffusion coefficient. P is defined by this thing. So there is a diffusion coefficient, then there is a advection velocity. So what you see is that depending on your this ratio, you get this term, and you find and you plot it down, and you what do you see is your spectral radius has this kind of form, and it depends on P. These are A, B, and C, and it's a complicated form. But if you start plotting them, and depending on your number of points, uh, you will see that there are some regions. See, there are some regions where your spectral radius goes higher than 1. But otherwise, if your P is positive, it is always lower than 1, no matter what discretization you do. But for small negative p values, with what does that small negative p value means? That your advection velocity is much higher than your diffusion, or it is much higher than compared to your discretization scheme. So diffusion is lower and your advection is very high. No, wait. So this thing, this gamma or whatever this graph, this Greek symbol is called, let's say gamma by u is a constant. But if you, and suppose that they are in the negative direction, so the diffusion happens in the negative direction of your advection velocity. If you choose a very high discretization, then your P will be a small negative number. In that case, you can go unstable. But otherwise, if you choose good discretization, then you will always converge. And that is where this, depending on the P value, the amount of depending on the P value, you so see if your P value is depending on the P value, it dictates that, the number of discretization that you have to do. So only for what do you say, smaller like P values less than uh, half, which is like that is the dictation of your grid size, right? If your grid size is if you increase your grid size such that you go into a negative higher than negative 0.5, then you are in a good condition to converge. Otherwise, it will not converge. But if P and if your gamma and U are in the same direction, then you're always assured to converge. Okay, so that is a reason. So you can actually look at to this. So P should be always higher than negative half, even if we have negative P values. Yeah, so we can apply the same method to multiple schemes, see if we can actually get into find something. Okay, but the drawback is that it is only valid when you have it only makes sense when the boundary conditions are periodic. Okay, that is an important limitation of this method. So this method kind of uh, is restricted to periodic boundary conditions, but that can happen in a lot of cases, and then we can use this Fourier decomposition of error. So nothing very fancy, but yeah, it's a nice way of exploring things. Okay. Uh, so this part was covered in the course. I'm not sure. Let me check. I thought that this was not covered. It was there. I think it might be there in later weeks. I might have skipped it. So Apur, was it there? He's not there now. Anyways, So I think we'll stop here. Let's meet later on. Yeah, thank you for joining. Yeah, thanks.